All right, problem number 4. It says calculate not standard cell. Just calculate the cell potential. It's not standard for a galvanic cell based on the following half reaction at 25 degrees Celsius. Whew. Okay, we're given these two half reactions again. They're reduction half reactions, but note here we're given the concentrations of those two things in solution. Our very first step is to write a balanced redox reaction. If we take a look at our reduction potentials, the more positive one is the one here at the bottom. So this is where our reduction is going to take place. So when we rewrite that equation, we're going to rewrite it exactly as it's written. And the standard reduction potential for that half cell is going to be negative 0.13 volts. Second, we need to reverse that other reaction to get our oxidation half reaction. So we're going to get solid cadmium, going to be losing 2 electrons here. Whoa. 2 electrons here. Our reduction potential becomes flipped. So we've got a positive 0.40 volts. We need to make sure that we are gaining as many electrons as we are losing, or combine these reactions. We're going to get CD plus PB2 plus. Our electrons cancel out. We're going to get CD2 plus PB. Our standard cell potential would be 0.27 volts. Woo! That's great, but we're not looking for the standard cell potential. We are looking for the cell potential when we've got these non-standard concentrations. Again, standard concentrations are 1 molar. So why did we do all of that? Well, if you use the Nernst equation at 25 degrees Celsius, the Nernst equation reduces to the cell potential is equal to your standard cell potential minus 0.0591 over your number of moles times the log of that reaction quotient. So to figure out what the cell potential is under these non-standard conditions, we know what the cell potential is under standard conditions at 0.27 volts. And if we subtract 0.0591 over the number of moles of electrons transferred, in this case 2 moles, times the log of our reaction quotient. The reaction quotient, remember, is products over reactants. Our product concentration was given to us as 0.010 molar. Our reactant concentration is 0.100. And so if we solve this, we are going to get 0.27 volts minus 0. Let's just divide this. We get 0.0295 log of 0.10. We then get 0.27 volts minus 0.02955 times, well, the log of 0.1 is going to be -1. And so essentially this is 0.27 volts plus 0.02955. And so our cell potential under these non-standard conditions is positive 0.30 volts. Whew. So let's compare the voltage under non-standard conditions to the voltage under standard conditions. Notice we've got an increase in the in our voltage. Now, to explain that, you can simply work through the Nernst equation as I've done here, or you can recognize, okay, let me look at my reaction quotient. My reaction quotient here is expressing the concentration of the products over the concentration of the reactants. And then as you think about this, the concentration of your reactants is greater than the concentration of your products. So your denominator is larger than your numerator, and so you get a number that is less than 1. We got 0.10. Reactant concentration is greater than your product concentration. And because of that, your denominator is larger than your numerator, you're going to have a reaction quotient that is less than 1. And when you take the log of your reaction quotient that is less than 1, you're going to get a number that is less than 0. Therefore, because we're getting a number that's less than 0, like we did here, you're essentially going to be adding to the standard cell voltage. And so you're going to get a non-standard cell voltage that is greater than your standard cell voltage. Okay, and then the last thing to sort of keep in mind is concentration cells. As you look at number 5, it says a cell has on its left side a 0.20 molar copper 2 solution. The right side has a 0.05 molar copper 2 solution. The compartments are connected by copper electrodes and a salt bridge, designate the cathode, anode, and direction of current. So this is a concentration cell because we've got the same solution, same metal here, but we have 2 different concentrations. Okay, I'm just going to draw a quick diagram here to help you sort of better understand this. We've got our 2 half cells here, our 2 electrodes, both of which are copper connected by a wire. Here's my salt bridge, boom, salt bridge. And in each of them, we've got a copper ion solution. The left-hand side is 0.2 molar. The right-hand side is 0.05 molar. So I'm going to do one of these. I'm going to put some more in here. It's more concentrated. Okay, so as you think about this, the current is going to flow until the concentration in both cells is equal or the same. And it's going to flow from the cell that has a lower concentration to the cell that has a higher concentration. Okay, and as we think about why that's going to happen, okay, and again, because we want concentrations to be the same, that means that the copper electrode on the left-hand side is going to be reduced. In other words, our copper ions are going to gain electrons to form copper metal. And because we're being reduced over here, red cat, this is our cathode. So cathode over here. Think about that. If this side over here is gaining electrons, these little copper ions are going to gain electrons, and they're no longer going to be ions in solution, but they are going to sort of gain those electrons and hook up to the cathode there as neutral copper atoms, reducing the concentration of the copper ions in that cell, which means that if we're having reduction occur over here, that we're having oxidation occur over here. So the solid copper is over here losing some electrons, losing some electrons to form greater copper ion in solution. So one of these is sort of dropping off some electrons over here and plopping a copper-2 ion into solution. This is going to happen until the concentrations are the same. Let's see, anox. This is going to be anode. Oxidation is occurring here. The direction of the flow, we want to think fat cat from the anode to the cathode. So electron flow is going to be in this direction. Whoop. Okay, and the big takeaway here is simply to recognize that, or to illustrate to you that under non-standard conditions, we're going to get a cell voltage that is different from standard conditions. Essentially, this is why we have to use the Nernst equation. Now, it's a great simulation I put on the website. You can use it to practice this, have fun,